Welcome back to linear algebra. In this video, we're going to be talking about dependence and independence. When you think about vectors in two-dimensional and three-dimensional space, the idea of linear independence is fairly straightforward. Two vectors are called linearly dependent if they form the same line or if they follow along the same line. And they are called linearly independent if they follow along different lines that are not the same and not in parallel. Our goal in this video is to extend that concept into our now arbitrary vector spaces and get a nice definition of how we can deal with linear independence and linear dependence. And we'll be able to build on that in order to work on some things as we go through the rest of the course. So let me get my head out of the way and let's dive into this definition. All right, so we need a vector space. Let's call capital V our vector space. We need a set, a subset of this vector space. We'll call it set S, and it's going to have n vectors in it that we'll name u1 through to un. And then we want to take a linear combination of the vectors in S. So C1U1, C2U2, all the way through to CNUN. We'll call this thing V for shorthand. And because V is a vector space, it's closed under linear combinations. So I know that V is an element of, vector V is an element of vector space, capital V. And the definition we're going to use here, if this linear combination vector V is equal to the zero vector, only when all of the coefficients, C1, C2, all the way through to Cn are all zero. If that is the only way to make V the zero vector, we say that S is linearly independent. If that is not the case, if there are values for C1 through to Cn that are not all zero, and you can still get that vector V is the zero vector, we say that S is linearly dependent. And let's take a look at a couple of particular vector spaces and a couple of particular sets of vectors so we can get a feel for how this is supposed to work. So let's take a look at the vector space P2. Remember, P2 is the set of all polynomials of degree 2 or lower. And from that set, I want to think about the vectors 1, x, and x squared. And we want to pick values for C1, C2, and C3 so that C1 times x plus C2, I'm sorry, C1 times 1 plus C2 times x plus C3 times x squared, which is really confusing if you've worked with polynomials in any other course, starting with 1 instead of 0, but we can make do. But we want this linear combination to be equal to 0. And we want this to be equal to 0 for all values of x. And one important thing that you learned in working with polynomials in a high school or college algebra class, pre-calculus, or whatever it happened to be called when you took it, the only way for two polynomials to be equal to each other is if all of the corresponding, the only way for two polynomials to be equal to each other for all values of x is for each of the corresponding coefficients to be equal to each other. On the left-hand side, the coefficients of this polynomial are C1, C2, and C3. On the right-hand side, the coefficients of this polynomial are 0, 0, and 0. So that's it. We know from working with polynomials in the past, the only way this is going to work is for these things to be 0. Let's take a look at another example that's going to involve a little bit more computation. Let's go to the Euclidean vectors, R3. Those are the ones you're more familiar with. It's always easier to work around those than other vector spaces. So in R3, I'd like to think about the set containing the vectors 1, 0, 0, 1, 1, 0, and 1, 1, 1. Once again, to think about whether this set is linearly independent or linearly dependent, our goal is to take a linear combination. So we'll have C1 times 1, 0, 0 plus C2 times 1, 1, 0 plus C3 times 1, 1, 1. And we want to pick values of C1, C2, and C3 so that this is equal to the 0 vector, 0, 0, 0. We know how to work with the Euclidean vectors. we can multiply C1, C2, and C3 into those vectors. We can add them together. And you will see when you do that, that you get C1 plus C2 plus C3, C2 plus C3, and C3. From here, two vectors are equal to each other if and only if the corresponding entries, the corresponding coordinates of the vectors are equal to each other. So we get that C1 plus C2 plus C3 is equal to 0. We get that C2 plus C3 is equal to 0. And we get that C3 is equal to 0. A system of 3 equations in 3 unknowns. There are a lot of really powerful tools that we learned in the first part of this course that we could employ here to try to break through this. But notice that this is actually going to be incredibly easy to solve. C3 is equal to 0. Substitute that into the line above. And you get that C2 is equal to 0. Substitute both of those things into the top line. And you get that C1 is also equal to 0. So we see that the only linear combination of these 3 vectors that gives us the 0 vector is C1 equals C2 equals C3 equals 0. And that's what it means for S to be linearly independent. Let's take a look at one more. This time we're going into R2 so that it's even easier to work with. And I'm going to take a look at 3 vectors, 1, 0, 0, 1, and 1, 1. And I want to, once again, determine if S is linearly independent or linearly dependent. And I do that by taking a linear combination, C1 times 1, 0, plus C2 times 0, 1, plus C3 times 1, 1, and set that equal to the 0 vector, 0, 0. Once again, using the properties of the Euclidean vectors, I can combine a bunch of stuff here. And I get that this left-hand side simplifies into C1 plus C3, C2 plus C3. And once again, 2 vectors are equal if and only if their components are equal. So this turns into the system of equations C1 plus C3 equals 0, C2 plus C3 equals 0. 2 equations and 3 unknowns. Just from that, you know that things aren't quite going to work as nicely as we would hope. All right. Pick a parameter for one of the entries. And I'm going to choose C3 equals the opposite of T, because you can see then that C1 is going to equal T and C2 is going to equal T. So for any value of T, T opposite of t gives us a solution. Generally speaking, whenever you are looking at this situation of determining if there are values of C1, C2, C3 that give you the zero vector, you are either going to find that everything equals zero is the only solution, or you are going to find that there are infinitely many solutions. There is not really any in between. Because once you have a solution, you can multiply both sides of the equation by any constant you would like, and you get another solution. It's just that when the solution is everything is zero, multiplying zero by anything you'd like still leaves you with zero. One of the interesting things about this particular problem is that it turns out any pair of two of the three vectors in this particular set would have been linearly independent. And that idea actually leads me to the last theorem here. Let's let V be a vector space, and let's let S be linearly dependent. Then we can pick one of the vectors in S, we'll call it U sub k, so that UK is a linear combination of the other vectors. That is, the vectors in S throw away UK. And the proof of this theorem is fairly straightforward. Since S is linearly dependent, then the linear combination C1U1 plus C2U2 plus through to CNUN is equal to zero with at least one CK non-zero. I don't know that they are all non-zero, but at least one of them is non-zero. And I'm specifically calling out the one that's non-zero as CK because I want to rewrite this emphasizing the CK-UK term. And I'm going to rearrange this equation so that CK-UK is on the left-hand side. And on the right-hand side, I'll just subtract everything else. So I'll have minus C1 U1. I'll have minus C2 U2. Skip K, but eventually get to minus Cn Un. And since Ck is non-zero, I can divide both sides of the equation by Ck and get these nice fractions. Minus C1 over Ck minus C2 over Ck through to minus Cn over Uk. These are all constants, so this is a linear combination of all of the remaining vectors. There we have it. Here's one more theorem. Let V be a vector space, and let S be a subset of V such that the zero vector is one of the elements in set S. In this situation, just with that fact is enough to determine that S is going to be linearly dependent. I would like you, as part of the practice problems, to take a look at this one. In older editions of our textbook, this was one of the homework problems. In newer editions, they have taken it out, but I think it's a very interesting one. So I would like you to take a couple of minutes and think about that, along with the suggested exercises out of the textbook. And I'll wrap up our discussion on linear dependence and independence here. And I'll see you in the next video where we start using these ideas of linear independence to find new ways to talk about the vectors in a vector space.